What we're jumping into now, and what you're about to jump into with your lab, is this idea of reflection and refraction. Okay? We have to, since we started talking about light, right? Light likes to bounce, light likes to bend. So what we're going to do in lab is a couple different things. Okay? The first of which we'll look at is this idea of reflection. Okay? Key word right here. Light bounces off. The law of reflection states that the angle of incidence is equal to the angle of reflection. Angle of incidence means the incoming ray. Angle of reflection is for the outgoing ray. Okay? And one of the things you have to think about is, where are those angles? Okay? Those angles are with respect to the normal. This is theta I. This is theta R. Okay? Incident ray, reflected ray. It's kind of like when you go play pool, those little diamonds, right? You ever notice those little diamonds that are on the edge? Okay? That's what you're aiming for when you have the angle in equals the angle out. But remember, it's always with respect to the normal. If you remember when we started talking about forces and we talked about a normal force, right? Normal means perpendicular. Okay? Normal means perpendicular. So there's the reflection. This is refraction. What does refraction mean? Okay? Refraction means bend. Okay? But now what happens with light, we're crossing some border. Okay? We're going from media 1 to media 2. Okay? Whoop. And we're going to speed up or slow down based upon that. Okay? And you kind of have to think of it, this is going to be just the opposite of, excuse me, just the opposite of what sound was doing. The more dense the material, the more that's going to slow the path of light down. So what does this look like here? Here's your incident ray, right? Your incident ray means it's incoming. Okay, there's your normal. Here's your theta I. Here's your theta R. And theta we just use to denote the angle. You know, it's just standard. Here's our boundary interface right here. There's our boundary right there. The normal is perpendicular to the boundary. Okay? And it's one of the things that we'll learn right here. It's like looking at the glass. The pencil looks all bent, right? Okay, because we're going from air to water. Okay, so the light is going to bend when it hits the water. Okay? There's an index of refraction, so we can kind of tell how things are going to bend. Okay? It's a measure of how much light bends when it passes from the vacuum of space with no hindrances to some medium. Okay? Could be water, could be glass, could be diamond. Okay? Each material, like a diamond or a garnet, or that's one of the ways they prove gemstones, right, is they look at the index of refraction for that piece to tell if it's real. What does it look like? This n, the index of refraction, is an n, equals the speed of light in a vacuum, c, divided by the speed of light in that substance, v. Okay? So is the number going to be always greater than 1 or less than 1? Does anything go faster than the speed of light? Not that we know of yet. Okay? So this number is always going to be greater than 1. N is the index. There's no unit since it's basically a ratio, right? It's got speed over speed. but it tells you a lot by the type of material. Here's a problem. The speed of light in one type of plastic is 2 times 10 to the 8th meters per second. What is the index of refraction for that plastic? Well, if n is this equals speed of light divided by the velocity, okay, remember the speed of light is going to be 3.0 times 10 to the 8th meters per second. Okay, that's not going to change. Okay, that's your C. Okay, so the index of refraction would be 1.5. Find the speed of light in water, where n equals 1.33. Well, what do you got? You know that n equals basically C over V, so what do you have? 1.33? 3 times 10 to the 8th over V. Solve for V that way. Find the speed of light in water. Okay, remember, n is the index, C is the speed of light in a vacuum, V is the speed of light in that substance. Now, a guy named Snell came along, okay, and was looking at these angles of incidence and the angles of refraction, and he kind of figured some things out, that how much those angles were, how much that angle of refraction was, depended upon, the type of material, your ends. Okay? Your ends. And remember, this I know is goofy, but these are thetas. Theta I, theta R. I couldn't find the little substitute on there. So N I sine theta I, N R sine theta R. What does that look like? What does that diagram look like? Okay? Let me see if there's a picture in here. Here's a picture, right? Okay, there's just working a problem. A ray of light in a liquid is incident upon a diamond at 45 degrees. The N for diamond is 2.42. If the angle at which it is refracted is 20 degrees, sorry, that's a degrees, 20 degrees, what is the index of refraction of the liquid? Remember, Ni sine theta I equals Nr sine theta R. Okay, a ray of light in a liquid is incident upon a diamond at 45 degrees. And what are you looking for? Incident. Incident, sorry, is 45, the angle. This is sine theta, sine 45. Okay. What's my N? 2.42. Okay. Start plugging them in. The hardest part is just simply trying to figure out what's what. Which of these variables are which. Okay. And I think I might have drawn that wrong. So take a look here. I don't know why this got turned. Right. Whoop. Now my board's going a little weird. Okay. Okay, so basically what's happening, we're going from water to diamond. Okay, does that make sense? I don't know what this black part was right here. This, I guess this is, yeah, this is the water. This is diamond. Okay. So is it speeding up or slowing down when it goes from water to diamond? This is one of the things that we'll look at with these N values here. Okay. One of the things you need to think about. If N goes up, what is the speed doing? If N goes up, you're slowing down a little bit. Okay? Does that make sense? Because you know when it's at 1, you're in vacuum. Okay? So if you go from 1 to a 2, you're slowing down. Other types of problems. If a light beam in air, where n is 1, hits a body of water, where n is 1.33, at 30 degrees to the normal, what angle was it refracted? Remember, what's the formula? Ni. Here, let me write that. Ni sine theta I equals Nr sine theta R. Okay? If a light beam in air, well, we got 1. It's a body of water. Well, there's 1.33 over there, right? Just start plugging them in. Start plugging them in. The only thing you might have to do is when you're solving for an angle, remember, when you're solving for an angle on your calculator, right, you have to go for the inverse sign, right? Okay? Remember, there's your normal. Your angles are always to the normal. Okay, so we went from air to water. Did we speed up or slow down? We went from 1 to 1.3. We slowed down. If we slowed down, did we go towards the normal or away from the normal? Well, our angle started at 30 degrees. It ended up at 22. We bent towards the normal. Okay, so one of the things you have to remember when we go from fast to slow, you bend towards the normal. Okay? Right? You're going from air to water. Fast to slow, you're bending towards the normal. Okay? Here's some other problems. You know, if the light beam in air has a body of water at 30 degrees to the interface, don't let us try to fool you. 30 degrees to the interface. That would be your 30 here. What angle do you want to know? Your angle that you want to know is always towards the normal. Always, always, always. You know we're going to throw you a curve here and there, right? Okay? Again, we're going from air to water. Are we speeding up or slowing down? We are slowing down, right? Our n's increased. When n increases, you're slowing down. If we slow down, okay, we started at 60 degrees, we ended at 40 degrees, right? We wanted to go on like that, right? But we bent towards the normal. Okay? Whoop. That's it. Okay, our lab starts tomorrow. We're going to start mixing some light and then doing some other things. So, thanks for listening.